Chapter 5, Section 1 is perpendicular and angle bisectors. Okay, there's two definitions we're going to use, equidistant and locus, and we have four theorems. Okay, one is the perpendicular bisector theorem, another is the angle bisector theorem, and the other two are simply the converses of both those two theorems. So, to start off, we have equidistant. All right, equidistant is when a figure is the same distance away from two or more figures. So, how we use that is our perpendicular bisector theorem here, 5, 1, 1. If a point is on the perpendicular bisector, so I've drawn that here. Right, this angle here is 90 degrees, so it's perpendicular. And if you notice, AB is 10.27 and AC is 10.27, so it's a perpendicular bisector. So DA is the perpendicular bisector. So if a point, D, is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So that means from D to B, that endpoint, it is congruent from D to C, this endpoint. And if you notice the measurements here, 12.35, 12.35. They're the exact same. It doesn't matter where the point is. Okay, I can take D here, this line is the perpendicular bisector. I can move it up and down, and notice the values here don't change, but the distances, that's what we're really looking at. This is the theorem. If it's on a perpendicular bisector, then the distance from that point to the end point stays the same. Notice 12.35, 12.35. I can go all the way down to the bottom here, 10.87, 10.87. It makes no difference. I can move it up and down on the perpendicular bisector, and the lengths are congruent. Okay, so that's the perpendicular bisector theorem. Okay, the converse of this says if a point is equidistant from the endpoints. So I say DB is congruent to DC. Then it is on the perpendicular bisector. So I can conclude that D is on the perpendicular bisector. So I can say AB is congruent to AC if I didn't know that. Okay. All right. Another definition here: a locus is a set point that satisfies a given condition. Okay. A point on the perpendicular bisector here would be a set of all points that are equidistant from the line to the endpoint. Okay, that's all a locus point. A better example of a set of locus points is a circle. All the points on the circle are the same distance from the center point on the circle. Okay, so how can we use these two theorems? Okay, all right, I just have a generic triangle here. Okay, and I say that triangle or this line AB, this line segment, is perpendicular and it splits CD in half. So CB is congruent to BD. Well, since it's a perpendicular bisector, I can therefore conclude that AC is congruent to AD by the perpendicular bisector theorem. So these two things are congruent. All right. All right. Another thing, using the converse, I say that AC is congruent to AD. Since these are congruent and this is congruent, they're the equal distance, and therefore I can conclude that this is 90 degrees and these two split into two equal segments. Okay, so how can I use this in a problem? All right, edit, and this is the converse theorem. I know these two are congruent, so therefore I can conclude that this segment here is perpendicular and it splits it at the midpoint, so it's a perpendicular bisector. Okay, so for instance, I say that this is 7.3 and I say that AB is a perpendicular bisector to CD. So that means that those two things are congruent. If I give you this, because this is the perpendicular bisector, these two things, by the perpendicular bisector theorem, AC has to be congruent to AD, so AD is 7.3. Okay. If I want to use the converse theorem, then I would need to be told, so let's say that BD is 16, AD is 36, and AC is 36. Okay, and this is a right angle. Since the distance here is 36 and the distance here is 36, then I can conclude this is a perpendicular bisector. So this segment is congruent to this one, so CB is 16. Okay, so that's how we use the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. We can tell things about their sides. Okay. All right. Now talking about distance and angle bisectors. Okay, so the angle bisector theorem states that if a point is on the bisector of an angle, so D here is on the bisector, because if you notice here, DBC is 31.2, so this angle is congruent to ABD here with this angle. Okay. So that's 31.29, this one's 31.29, so that's the angle bisector. So if I have a point on the angle bisector, so D here is on the angle bisector, then that means it is equidistant. All right, remember distance has to be a perpendicular line to the sides of the angle. So I have the angle here, this side of the angle, and this side of the angle. The distance from D to this angle and the distance from D to this side is the same, 6.57 or 6.56. So that's what the angle bisector theorem says. If a point is on the angle bisector, then it is equidistant from the sides. Okay. Now the converse of that says that if a point, let's move this over. If a point in the interior of an angle is equidistant, so I say that it's congruent here and congruent here to the sides, then it is on the angle bisector. So I can conclude that this angle is congruent to this angle. Okay. All right. So how can we use this? And notice real quick, if I change the angle here. All right, the angles are the same, so it's an angle bisector. Notice the distance, 5.96, 5.96, stays the same. Okay, that's what the angle bisector says. All right, angle bisector theorem. If it splits, then a point, the distance from this point to a point on the side is the same as this from that point to a point on the other side. Okay, and the converse says if they're the same distance, then the angles have to be the same. Okay. So we look here. Let me label these points real quick. So I have what looks to be a triangle, or multiple triangles. Okay. Now, if I said that triangle, or that angle BCD here is congruent to DCE, so this is an angle bisector, then I can conclude that BD is congruent to DE by the angle bisector theorem. Okay? If I have that BD is congruent to DE, and this is a 90-degree angle, and this is a 90-degree angle, so that means it's the distance, then I can conclude that this angle is congruent to this angle. So the converse of this. Now, don't just assume when I'm using the converse it has to be the distance. So from D to E, it must be perpendicular. From D to B, it must be perpendicular. Okay? They could still be congruent and not have the same 90-degree angle here, 90-degree angle here. So that's the big key. The distance from D to E, so that means it has to be perpendicular, and the distance from D to B has to be perpendicular. If they're the same, then these two angles are congruent. All right, now let's put some numbers to it. So let's say that these are 90-degree angles and that this angle is congruent to this angle, and I say that this is 12.8. Therefore, I can conclude, since it's an angle bisector, and these two segments represents the distance from D to the side and D to this side, that they must be congruent. So this is 12.8. Okay. All right. Now to work backwards. Let's say that I'm told that this is 90 degrees and this is 90 degrees, and this is 74 and this is 74. Since they're both 90 degrees, that means it's the distance from D to that side and D to this side, and they're both congruent. So if the distance is the same from D to this side as the distance from D to this side, then that means that D is on the angle bisector, so this angle is congruent to this angle. Okay. All right. So that is Chapter 5, Section 1. Okay, we had the two definitions: equidistant, which means one point or an object is the same distance to multiple objects. A locus is a set of points that satisfies a given condition. All right, and then you have the angle bisector theorem, the perpendicular bisector theorem, and the two converses of those.